Section: Introduction and Related Work. In this section, we discuss position encodings, PEs, that provide information about the locations of tokens in transformers. These encodings are crucial for performance because standard attention treats inputs as a set, which does not account for the order of tokens. Initially, we used absolute position encodings, APEs, which add fixed position embeddings to tokens. However, we have shifted to relative position encodings, RPEs, which introduce a learnable bias based on the distance between tokens, allowing for better generalization across different sequence lengths. To overcome the limitations of both APEs and RPEs, we have adopted rotary position encodings, RoPE. RoPE enhances the way we handle queries and keys by dividing them into two-dimensional blocks and rotating these blocks based on the token's position. This method allows us to maintain the advantages of both APEs and RPEs. Specifically, RoPE transforms each query and key independently, which simplifies the caching of key value pairs during processing. Additionally, the rotation angle for a query key pair depends only on their relative positions, improving generalization across varying sequence lengths. We also introduce string, a more general algorithm that builds on RoPE and incorporates its features while providing a unified theoretical framework. String is particularly beneficial in robotics, where efficient representation of 2D and 3D tokens is essential. We demonstrate string's effectiveness by integrating it into vision transformers, VITs, leading to significant improvements in open vocabulary object detection and various robotics controllers. Our key contributions include the introduction of string, a new family of position encodings that maintain both separability and translational invariance. We rigorously analyze string's theoretical properties, proving its generality compared to RoPE, and we provide efficient computational implementations. Our results show notable accuracy improvements across different models using string in various robotics and vision tasks. Section Summary. In this section, we discuss the evolution of position encodings in transformers, highlighting the transition from absolute position encodings, APEs, to relative position encodings, RPEs, and the introduction of rotary position encodings, RoPE, which enhance performance by combining the strengths of both APEs and RPEs. We then propose string, a more general position encoding method that maintains separability and translational invariance, demonstrating its effectiveness in robotics applications and various vision tasks. Section: String, Separable Translationally Invariant Position Encodings. In this section, we introduce string, which enhances the way we modify queries and keys based on their positions. Our aim is to ensure that the changes in the dot products between queries and keys depend on the difference in their positions. String is a more general and effective algorithm compared to RoPE, which we will explain further. String is defined using a matrix exponential, which is calculated through a series expansion. We denote the kth coordinate of a position vector as the kth element of that vector. When we refer to commuting skew-symmetric generators, we mean that a specific set of matrices satisfies certain properties. We can parameterize these mappings in various ways, which we will illustrate later. String is versatile because it can represent a wide range of translationally invariant position encodings using matrix multiplication. RoPE is a specific instance of string, derived from a particular choice of generators. We can see this by examining the generators used in RoPE, which relate to rotational frequencies. Despite string's generality, the way we parameterize the string matrices can be computationally intensive, especially when dealing with many tokens at different positions. This can lead to high time and space complexity, particularly when the positions vary across different training examples. Therefore, we aim to find more efficient implementations of string that remain more expressive than RoPE. We note that for any string encoding, we can find an orthogonal matrix that simplifies computations. This matrix can be learned once and reused across all training examples, which reduces memory and time requirements significantly. RoPE, in this case, is a special instance of string where the orthogonal matrix is simply the identity matrix. We also explore a specific parameterization called Cayley string, where we use a learnable antisymmetric matrix. This approach allows us to compute position encodings efficiently without needing to invert matrices. Interestingly, string consistently outperforms RoPE in our experiments, likely due to the explicit learning of the basis change through the orthogonal matrix, which enhances performance. In contrast, when using linear attention variance, the inclusion of a learnable matrix increases the network's capacity. Additionally, we present circulant string, another efficient algorithm within our framework. Circulant matrices have unique properties that allow us to define our generators in a way that enables fast computation of position encodings using the fast Fourier transform. This method is particularly effective for large, high-dimensional datasets and performs well in spatial applications. Section Summary. In this section, we introduce string, a general and efficient algorithm for position encoding that modifies queries and keys based on their positions, improving upon the existing RoPE method. String allows for various parametrizations, including Cayley string and circulant string, which enhance computational efficiency and performance in tasks involving large datasets. Section: Learnable frequencies with string. In this section, we explore learnable frequencies using string. We note that the string generators are generally learnable. For Cayley string, the frequencies that define angles for RoPE and the antisymmetric matrix are learned, while in circulant string, the scalars are also learned. Next, we discuss further generalizations of string. For extension 1, we introduce O-time string. We have previously followed RoPE by applying position encodings through matrix multiplication, but we can relax this assumption while maintaining separability and translational invariance. We can transform tokens by using the outer product with position feature vectors. Here, the outer product is denoted by O times, and the vectorizing operation flattens a matrix into a vector. This means that when we vectorize the outer product of the position feature vector and the token, we get a specific relationship between the elements of these vectors. If we use learnable frequency vectors, we find that the inner product of the position feature vectors is a function of the difference between their positions. We call this new position encoding variant O-time string, which is different from previous RoPE-like methods. For extension 2, we consider general transformation groups. After focusing on translational invariance, we ask if string can be adapted for other continuous transformation groups that might be better suited for different types of data. For example, we might want a position encoding that is invariant to rotation. We recall that a Lie group with parameters represents a group of differentiable transformations. The identity element corresponds to no transformation. A canonical coordinate system maps Cartesian coordinates to a new system, allowing us to express transformations in a simpler way. For one-parameter Lie groups, we can derive these systems analytically, and for abelian groups, they can be more generally defined. For instance, in 3D space, we can use spherical coordinates to represent rotations, which simplifies the transformation process. By replacing Cartesian coordinates with their canonical counterparts, we can adapt string to create position encodings that respect these broader invariances. Finally, we present a thorough empirical comparison of string with RoPE and vision encoders that use regular apes. We begin with general non-robotics experiments, then move on to test string for 2D and 3D object detection, and conclude with robotics manipulation experiments. Section Summary. In this section, we explore learnable frequency variations of string, including Cayley string and circulant string, and introduce two extensions, O-time string, which utilizes outer products for position encoding, and a framework for adapting string to other continuous transformation groups, enhancing its applicability to various data properties. We also outline our empirical comparisons of string with RoPE and traditional apes across different experimental setups, including robotics applications. Section: General Experiments, Classification and Retrieval. In this section, we conducted experiments to evaluate string for image classification tasks using the ImageNet 2012 and Places 365 datasets, employing the Vision Transformer, VIT, as our base model. We compared string against RoPE and RoPE mixed, which we abbreviated to RoPEm, as well as circulant string and Cayley string, referred to as circulant S and Cayley S. The results, displayed in a table, indicate that string consistently outperforms the others. Specifically, for ImageNet 2012, the top two models are strings, which also achieve the first significant gains over 1% compared to standard VITs, with only a minimal increase in trainable parameters. Next, we enhanced the WebLI dataset, which contains 10 billion image text pairs in various languages, by processing a 60 million image subset to create a 3D representation using Depth Anything v2 for depth estimation. We filtered out images where the indoor fine-tuned model struggled, such as those with overlays or large outdoor scenes. We then applied contrastive learning to the text and visual representation pairs in the WebLI 3D dataset, aiming to maximize the similarity between matching pairs while minimizing it for non-matching pairs. This approach allows for open vocabulary detection and classification by comparing text embeddings of all potential classes with those of the visual representation and selecting the closest match. Our comparisons against the baseline are shown in another table, where Cayley string emerges as the best performer, followed by circulant string. For open vocabulary object detection in 2D, we demonstrated string's effectiveness in localizing 2D bounding boxes on standard RGB image benchmarks. We used the official OWL-VIT implementation as our baseline, which employs a standard vision transformer with lightweight classification and localization heads. A table compares the baseline with rope and string variants, and we followed the standard training pipeline for the B32 backbone using clip loss. Even in this favorable 2D detection setting, Cayley string achieved the best overall performance. We also tested string for open vocabulary 3D object bounding box prediction, modifying the output to include the full pose and 3D size of the bounding box. We initialized our model's vision and text towers with weights from the WebLI 3D dataset and replaced the IOU loss from OWL-VIT with an 8-corner vertex loss. We trained on a simulated dataset of 4 million images with ground truth 3D bounding box labels, holding out 80 images for evaluation. The 3D intersection over union values for various models are presented in a table. Strings provided significantly more accurate predictions for smaller, harder to localize objects compared to the baseline and rope. For VIT, circulant string was the best, showing a 1.5% improvement over the best rope variant, while for VITD, Cayley string led with a 2% improvement. Lastly, we evaluated string's performance on dexterous robotics tasks using Aloha 2, a bimanual gripper setup in the Aloha Unleashed simulation environment. We trained a transformer-based neural network with diffusion policies on human demonstrations of 12 tasks, utilizing images from various camera positions. Our results, summarized in a table, show that string achieved the highest success rate across 11 out of 13 tasks, demonstrating its effectiveness. Cayley string consistently outperformed other methods, achieving superior results on average and converging faster than the alternatives. Section Summary. In this section, we evaluated string for image classification on ImageNet 2012 and places 365, achieving the best results with significant gains over standard VITs, and we also demonstrated its effectiveness in open vocabulary object detection in both 2D and 3D settings, outperforming baseline models. Additionally, we tested string in a simulated robotics environment, where it achieved the highest success rates across various dexterous tasks, showcasing its superior performance and faster convergence compared to other methods. Section: Real-World 3D Robot Manipulation, KUKA. In this section, we demonstrate that string outperforms other methods in previous tasks by applying it to 3D data, leading to new state-of-the-art robotic manipulation policies. These policies utilize depth information and are implemented on real hardware. String is well suited for this application as it can handle data with general coordinate vectors associated with tokens, such as 3D data. We assessed string using the vision encoder of a generative policy based on energy-based models, deployed on a KUKA industrial robot arm. The closed-loop feedback policy processes RGBD images and is trained as a generative model through imitation learning. The architecture includes a diffusion transformer and a 3D encoder. We trained the policy using a mix of scripted and teleoperated data for 3 skills: pick, place, and handover, focusing our evaluation on the pick skill with a variety of objects. Each evaluation was conducted as an A/B test over 50 trials. We explored 2 methods for incorporating depth into the policy. Our results showed that the 2D baseline without depth input achieved about 65% performance. When we added depth using surface normal maps, performance dropped to around 42%. However, using 3D string improved performance to 53% and 74% in scenarios with and without normal maps, respectively. In our first approach, we created a surface normal map from depth input, processing both RGB and depth data through shared embedding layers. The final vision embedding was generated by fusing these embeddings. However, this method negatively impacted the policy's performance, likely due to noise from depth sensors affecting the normal maps. In the second approach, we calculated the height for each patch by averaging depth values, then fed these 3D patches into the transformer with positional encoding from string. This method improved the success rate compared to the 2D baseline and mitigated the negative effects of noisy normal maps. We utilized circulant string for a more compact computational footprint, as more complex methods faced memory issues. To further compare string with the baseline, we conducted out-of-distribution evaluations on the real robot, varying lighting, adding large distractor objects, and changing the table height. We tested multiple variations for each setting. Our findings showed that 3D string policies consistently outperformed 2D policies across all scenarios. For example, with large distractors, the 2D model's performance dropped from 65% to 57%, while 3D string maintained around 74%. In lighting changes, both policies experienced performance drops, but 3D string showed better resilience, especially in table height variations, where it achieved about 50% compared to 10% for 2D policies. Overall, our results indicate that 3D string policies are robust to various changes and significantly outperform 2D policies. We also included a sample episode from the on-robot evaluation of the string generative policy for illustration. Section Summary. In this section, we demonstrate that our string method outperforms traditional approaches in robotic manipulation tasks using 3D data, achieving state-of-the-art performance on a KUKA robot. Our evaluations reveal that incorporating depth information significantly enhances the robustness and success rates of the manipulation policies, particularly in challenging out-of-distribution scenarios. Section. From 2D to 3D with string. In this section, we have shown that simply adding a depth signal does not always enhance performance, as demonstrated in our previous work on the normal map approach. However, string not only improves performance but also has a unique capability that other methods, like adding depth as an extra channel, lack. String can be trained using a standard 2D pre-trained model. This is possible because string integrates depth by adjusting a regular attention matrix, which separates the 3D specific parameters from the main 2D framework. All our training sessions, as discussed in the previous section, began with these pre-trained 2D models.